Good morning. This is the last lecture of the fourth module, which is also the last module. What is more to learn in thermodynamics? So we'll stop it. We'll take a little time to talk about that. So, for some questions that were pending since yesterday, let's take those up first. There's a question about what are the materials used in boiler and turbine. If you look at coal-fired boilers or oil-fired boilers, the tubes carry the water and these are subjected to high pressures. And by high pressure meaning whatever the pressure we get in the thermodynamic analysis, that is the pressure of the water inside the tubes, and this could be anything like, for small boilers this may be about 100 bar, and for large power boilers these days 280 bar, 300 bar is not uncommon. The thing is, because you have such high pressures, we need to make whatever the tube or the cylinder or the container whose diameter is small because of stress analysis. If you recall your solid mechanics, that larger the diameter, the stresses increase in proportion to the diameter, and the thickness of the wall that you require to make that device keeps increasing. So these devices which are at high pressures, if it's just a vessel or a tank, that is called a pressure vessel. And all these parts in a boiler or in a power plant or any other cycle which are subjected to high pressures, these are called pressure parts. The common materials that are used, these are lots of carbon steels of different types. And it's not just the fact that they are of this type of a material, but also that the way we make these affects their quality, also affects their life. So most of these things, they are firstly made out of small diameters. So diameters are relatively small. Of the the tubes in which water is boiled and evaporated, those tubes could be something like maybe 50 to 70 mm diameter. And the pipes that carry the steam from the boiler to the turbine, these could be like 350 to 400 millimeters in diameter. And to get the best mechanical properties out of this, these are made by hot rolling. That means you make a tube which is heated up, and then you first extrude it, and then you expand it, turn it, bend it, everything while it is hot, what you have learnt in metal forming, and that's how we get these tubes. So we cannot transport very long tubes to the site, so these tubes are made in lengths which are transportable, which is the length of a railway freight wagon. So all these tubes go to site, and at site then these tubes are put together and welded by hand. After welding is done, they are radiographed to see if there is any defect, and after that they are finally filled with water, which is pressurized more than the design pressure, what thermodynamics told us, to make sure that there is no leak. So that's what is done. Most of the tubes and pressure parts, these are of carbon steel. And how we selected these is that we needed to go to the temperatures that our cycles are telling us, like 560, 600 degrees Celsius, that type of temperatures. And our objective is that they should have strength and integrity at that elevated temperature continuously, year after year, for maybe 20, 50, 30 years. That is the whole thing. So that's what's done in boiler tubes. The turbine story is quite different. Okay, when I talk of boiler here, this boiler includes the fossil-fired power plant. It also includes a combined cycle power plant. If you have, I'll just explain what a combined cycle power plant is. We come to the turbine now. First you have the steam turbine. And these are alloy steels. Alloy steels for the shaft and the rotating parts, the shaft, blades, and rotating parts, and types of steels for the casing, the stationary parts. The real high-tech part are these rotating parts, because they are not just at high temperature, but they are also rotating, they are transmitting torque, and if you got a lot of blades on it, they would also be vibrating. So these are alloy steels. Typically there will be tungsten, vanadium, chromium alloys, and almost all of these are made by hot forging. Then they are machined and finally assembled to make a complete rotor. The casings are produced by casting, and after that they are machined, the blades are put in it, and the turbine gets done. So this is the material for steam turbines. Gas turbines, the temperatures at which they operate are much higher. So this temperature we are saying is limited to 565 degrees Celsius, the highest anywhere. And I mentioned that there are efforts to design it for a temperature of 710 degrees Celsius. So what happens here is steels are of no use. They do not maintain their strength at this elevated temperatures, and so the materials that are used here are various type of nickel based alloys, nickel and cobalt alloys. Make such large components on a big scale is something what technology development is all about. So that's being researched now. It will be some time before we get that the high temperature parts of the turbine will be made out of these. Examples could be, say, what a family of materials called Inconel, different grades of Inconel that is there. And once the temperature in the turbine after expansion has reduced, then we make parts out of alloy steels. Gas turbines have an entirely different story, because the temperatures here, as I mentioned, are much higher than this. 1400 degrees Celsius, 1600 degrees Celsius stationary gas turbines are already in use, and there are gas turbines with up like 1800 degrees Celsius. These temperatures are above the melting point of either nickel cobalt alloys or any steel alloy. So it is not just enough to make the material and the blade, but we also have to actively have a method of cooling it. Otherwise, it will just melt away. So what is done is that as the flow takes place over these turbine blades, this is a typical sketch of a turbine blade. What is done in this blade is that these are hollow. At the base also they are hollow, and they sit on the rotor. So this is the shaft. This shaft is also hollow, and some of the air from the compressor, say about 700 Kelvin, 800 Kelvin, 900 Kelvin temperature, instead of going to the combustor, bypasses that, is pumped through the passage in the shaft, comes in, connects with openings inside the blade, comes into the blade, moves through hollow passages inside the blades, comes out either from the top, or there are small holes on the surface of the blade from which this air comes out, and what it does is that this air goes over this, and right next to the surface forms a small blanket of cool air. So if you have to take a top view of this, one can say that this is the blade, these are the passages, and say here and here we were throwing out air over this. So this air came out and it went over there, this air came out, the flow over the turbine blade is like this. So this cold air is going over there, and outside this is the hot gases that are flowing over here. So the temperature here is what I mentioned at 1600, 1800 degrees Celsius. This air that is coming out is about 900 Kelvin or something of that order. And so the surface of the blade has, some air is also put out to the back part here. So this is sort of an open here. So there you have a blanket of cold air surrounding this blade, so that the material temperature in this does not go anything like 1000 degrees Celsius or even less than that. To further reduce heat transfer to the blades, one more thing is done. So these blades are all made of nickel cobalt alloys. Okay, so that's one. The second thing, they have a small thin coating on the top, few hundred micrometers thick, and this coating is made of certain ceramic, typically zirconia oxide. Ceramics have very poor thermal conductivity, so they reduce the amount of heat that will go into the blade. So we like to have that. The trouble is, first, ceramics are very brittle, and in a machine like this, if it comes off, that's a problem. The second thing is, if the blade is made of nickel and cobalt, and this is zirconium dioxide, there is no way that we can make ZrO2, zinc of zirconia, to stick to a nickel cobalt alloy. So the process of making zirconia substrate on a nickel cobalt alloy, this is extremely complicated, and we build layers and layers of different elements which stick to each other, and the last element in that is zirconia oxide. So this is so this whole thing, casting of this blade is a very sophisticated technology. That to get better mechanical strength, you do not like to have grains in the material like you've learned in your, say, casting or manufacturing processes. So they try to make this and cool it in such a way that the whole blade does not have grains but is a single crystal. That has very good mechanical properties. Then there are cooling passages, and then there are ceramic coatings on top of that. So gas turbine blades, aircraft engine blades, especially in the first 2-3 stages where temperatures are very high, this is what is being used. And the research that people are doing is that can we make the entire blade out of ceramic? And that's a huge challenge, because ceramics cannot be processed by any of the conventional manufacturing techniques that are taught in a typical manufacturing course. So that's about blades used in turbines. So that was one question. The next question was, what about supersonic flow in a nozzle? Hey, so this is what it is. When you say supersonic flow, what we mean is that the local velocity is greater than the local speed of sound, or c. And I'm using the word local because if you have, say, a nozzle, as the flow goes through it, its temperature is changing. So when the temperature at different locations is different, the local speed of sound is also different. So the Mach number, we have defined it as the velocity of the fluid divided by the local speed of sound. Now the reason why this thing comes up in the context of nozzle, and I'm taking it here, say, is that if you have a nozzle, which I have drawn like this yesterday, the flow goes in there, it comes out at a higher velocity, so pressure decreases, velocity increases, and that behaves like a nozzle. But what will happen if at some point, so we are assuming firstly in this, that everywhere Mach number is less than 1. That means this is the flow is subsonic. This behavior is correct. And the same is case with what we do for a diffuser yesterday. If you have a passage in which area increases, and it need not be a passage like this. I showed you yesterday that if we make a turbine blade like this, 2 consecutive blades, they produce, you can make the shape in such a way that the areas could be equal, or areas in the direction of flow could be decreasing, or areas in the direction of flow could be increasing. Either is possible. So here also, when we said that the flow goes in, pressure increases and velocity comes down, we have also assumed here that this is a subsonic flow. The opposite happens if the flow is supersonic. So this begins to behave like a diffuser, and this starts behaving like a nozzle. So what happens is really is that if you have a converging nozzle passage, say it is like this, and at this point we have Mach number equal to 1, then if you further decrease the area, it will not behave like a nozzle, but it will behave like a diffuser, and so pressure will start increasing. So now you ask that, well, I want to accelerate the fluid to an even lower pressure than what I could get here. I can't get this. Then what you do? Then you put a diverging section, and this part behaves like a subsonic nozzle, and this part is designed to behave like a supersonic nozzle. So what happens is that in this part we say Mach number is always greater than 1. We are accelerating it even more and more. So as Mach number and the area is, then here pressure will continue to decrease and velocity will increase, but this is a precondition for this behavior to take place. So to accelerate fluids to velocities much greater than the Mach number, local Mach number, possibly a combination of these two is required. The opposite happens here, that if we want to decelerate the fluid, a supersonic fluid, then this work will not do the job. A passage like this, if Mach number is greater than 1, this will start acting like a diffuser, velocity will keep going down in the direction of flow, and pressure will increase. The thermodynamics is the same, and we have not gone into the detailed thermodynamics of it, but the thing to remember is that as there is no discontinuity in the properties, conservation of mass and energy, the way we have learned, will apply. All these flows, in the ideal case, as we have discussed, these are all isentropic flows. And we have seen yesterday how we could not isentropic. It is a hugely irreversible process. S will increase, and so the isentropic flow condition can be done before the shock and after the shock, but not across the shock. We will not go into full details of what shock is. It's a whole different topic by itself. That there is the need, the requirement. We will have a separate module on this type of flows. But from our perspective, what we have learned in thermodynamics, this is fine. That we could get we could say that there is a nozzle and expanding it to a pressure where Mach number actually becomes more than 1. But thermodynamics does not tell us what the shape of it we have to get from compressible flow thermodynamics. So that's the thing about supersonic flow in a nozzle and a diffuser. The third question was about the compression ratio of an Otto cycle and a diesel cycle. Okay, so let's take up that. Detailed analysis of the cycles I will just describe in a few minutes, but I will not go into the detailed arithmetic of it. It is there in everywhere on the books on the web. You can see the full detailed derivation. What I have done here is just displayed the final formula. And now let's be clear, what is it that we are talking here about? We are looking at what I started discussing yesterday as air standard cycles. We did not have, firstly, these are all reversible. And we said yesterday that the working substance behaves like an ideal gas. We made a differentiation between what happens at the exhaust versus the cooling process. The cooling process is replaced by exhaust and by the intake. So air standard cycles it's a closed cycle, unlike the closed system that we have looked at, and real cycles are open systems. Because after the combustion is done, and of course the heating is replaced by a combustion process. So those are all the major differences between real cycle and air standard cycle. 3 major differences, and you should keep that in mind. And the reason we convert this real cycle into an air standard cycle is because it gives us a very quick and easy way to do the analysis and come up with some very quick ballpark numbers. But remember, this is an idealization, and the real cycles will be quite different and definitely less efficient than what these numbers tell us. In a course like this, we don't go into analysis of real cycles. We will just look at the first order analysis of these practical cycles. So these are the formulae. Thermal efficiency of Otto cycle is 1 minus 1 over R to the power K minus 1, where R is called the compression ratio. So what is compression ratio? We just take in this cycle is that we have a cylinder piston arrangement where the piston moves between this extreme position and this extreme position. And this is a standard machines, whether it's a compressor or whether it is a reciprocating internal combustion engine. So this is called the top dead center. And this is called the bottom dead center. And this much volume got compressed to this. So the ratio of this is called the compression ratio. So we can say this is volume at the bottom dead center divided by volume at the top dead center. It tells you how much you compress that gas. And if you look at the complete analysis of this cycle, the air standard Otto cycle will look like this. I am plotting V here and pressure here, and we say when the piston goes up and down, how does pressure vary, and what is heat transfer in each process, what is work transfer in each process. This is what we want to know. So what happens here is, in the compression process, we start from say here and we reach a point over there. This will be a solid line because I'm showing that these are ideal processes, but right now I'm just showing this. This is state 1, this is state 2. Then the ideal cycle, we have constant volume heating. So from here it goes and gets to state 3. This is constant volume heat addition. And after that, the piston has to come back to its original position, so it expands from here and comes back to this state, which is 4. And from 4 to 1, this was 1, 2 to 3, and 4 to 1 is again a constant volume Q out, cooling process. So this cycle and whatever is the substance inside this, and in all these cycles we assume that that substance is an ideal gas. So PV equal to RT is the equation of state. This can be applied. This is isentropic process. This is an isentropic process. And we can start doing the complete analysis from everything that we have learned. Process by process we write the equations and we say this is from process 2 to 3, this is a closed system. We write Q23 is W23, which is 0, plus U3 minus U2, which is CV0 T3 minus T2. So similarly, every process can be written in terms of Cp, CV0 and the temperatures. And then the net work output we can calculate that there was no work here, there is no work here. So the work output, net work output is W324 minus W12. And the heat input to the system was happening between Q23, and this is the net work of the cycle. So the ratio of this net work Wn divided by Q23, this is the thermodynamic efficiency of the air standard Otto cycle. And when you solve all these things by putting all these T's and CP's and CV's, we get the relation which is the first equation here, this one. 1 minus 1 upon R, k to the power, R to the power k minus 1. So this is the exponent. When you keep increasing R, gradually the efficiency goes up. As R gets higher and higher, the thermal efficiency doesn't increase that much. The benefit of pressure is getting lost. The second part was what happens in a diesel cycle. And here the story is slightly different. But the heat addition now is at constant pressure. So it goes there, and this is heat addition at constant pressure Q3. After that, we have exactly the same story. Expansion, which is isentropic, this was isentropic, and then a constant volume cooling. So these two processes and the cooling process are the same features as the Otto cycle, but this, which is the diesel cycle, the heat input is at constant pressure. So one cycle was heat, this is heat transfer constant pressure. The earlier cycle was heat transfer at constant volume. The Carnot cycle required it to be at constant temperature. That we argued yesterday is not possible. Point or this point or that point. That's a choice we have to make in addition to this and this distance. So first is the compression ratio R, which was again V1 divided by V2, or you can take V4 by V2, doesn't matter. The second, cutoff ratio, that is, this is defined as V3 upon V2. And when you do all the, again the same concept applied, we look at each to it. This is a closed system, and ideal gas is the working substance again. And when you do all of that, we get a formula which is like the second one here. Thermal efficiency is 1 minus 1 upon R to the power k minus 1. So this part is same as the Otto cycle, but now we have part sitting there where RC, which was the cutoff ratio, that has come in. So depends on what RT1 takes and begins to compare these two. But in general, if you just take these two and see which has got efficiency, it will turn out that the Otto cycle efficiency is slightly greater than the diesel cycle efficiency. But there is a little problem here. Otto cycles use which is in the range of 7 to 9 or 7 to 10, not more than that. And that's because what in this cycle, in the real cycle, is that we have an intake stroke which starts from here and it takes in the substance, and what it intakes is air plus vaporized fuel, a fuel vapor mixture. And then it is compressed to this point where the temperature is T2. And this T2 is less than the auto ignition temperature of this mixture. Otherwise, it can explode by itself and the rest thing can happen. And for that reason, the pressure ratio here is kept 7, 8, 9 in that type of range. In diesel cycles, what we have drawn here, the intake stroke is there when it takes in only air. So there is no danger that you can compress it as much as you want. There will be no explosion or no ignition. So compression ratios here could be anything from 14, 18, 20, even 22. So the temperatures here, T2, in the diesel cycle will be much larger than the temperatures at the end of the compression process in the Otto cycle. So that gives an advantage to diesel cycles, that because of this higher temperature at which then heat input takes place, overall the average temperature at which TH takes place is greater for diesel cycle than for Otto cycle. And that's why diesel engines in general have higher efficiency than Otto cycles. To complete the real life treatment, air standard cycle is what we drew here. The real cycle gets an additional thing. It takes in air, then compresses it, goes through it, and then it goes back over there and comes back to this state. So this we can call it zero state. Intake, outlet, there are two strokes. Then there is one stroke for compression and one is for power stroke. So each stroke is 180-degree rotation of the crankshaft. And so to take 4 strokes, you need 2 revolutions. There were 2-stroke petrol engines. I won't go into the details of it, what the problems are. There also you do the same thing. You got 2 more strokes sitting over there. But those are now pretty much on the way out because of the pollution effect and the lower thermal efficiency. But 2-stroke diesels are very much alive in big numbers, and all the big engines are all diesels. The next thing you should remember is that it is the same engine which, instead of burning fuel as a petrol vapor, is also used with natural gas. And this ignition here happens by putting a spark into it, which will cause it to explode. So a gas engine is essentially a spark ignition engine, but in many cases in our country, when diesel engines got banned, many people tried to convert a diesel engine into a spark ignition engine. The last thing I will speak about this is that the idea that it can explode by itself is now being researched, and we say, well, what we will do is we will compress it to a higher level so that it explodes by itself and it continues by itself. So I don't know spark plug. But such engines are not yet anywhere in the market. They are in the research laboratories. There is no practical way of exactly controlling when it will explode. That is one of the challenges. Research is going on. We do not know if and when it will come in the market. The important thing to remember is that a vast majority of the horsepower that you get is from diesel engines. Petrol engines are very largely used for 2- and 4-wheelers, and in some cases for some types of, say, boats, boat propels of boat engines, and some generators. The capacities are relatively modest. 200, 300, 400 horsepower is about the upper limit to which one starts getting these engines. Diesels, they generally do not go to very small sizes, but on the upper side, the biggest diesel engines are like 1 lakh horsepower. And these are used largely in marine propulsion. Almost all your generator sets, except the very small ones, they are called diesel generators because they are diesel engine coupled to an electric generator. And wherever in your city you see a exhaust pipe coming out, be certain that it starts off in a box which has got a diesel engine working inside it. Because of cell phones. Every cell phone tower, if it doesn't get reliable electricity supply, has its own diesel generator. It runs it, provides electricity for the electronics and also electricity for keeping it cool, which is to run an air conditioner, and across the country there are more than 1 lakh cell phone towers using diesel engines. So you can think that cell phone, which was not such a great thing as far as environmental effect was concerned, has had a huge impact on the diesel consumption in our country. So those were the questions that were already there. If there are any more questions, we will take those up. So you can keep posting those questions as we go on. I will now pick up what I thought I will do today. And before I summarize the course, I'm going to solve 2 problems. Just to illustrate how we should go systematically solving a problem. The process I've already given in assignment 2, where I stated a problem in very general terms. There were no numbers in it. I did that for purpose, that quite often I see that students get stuck with the calculation and forget what the concept was. So my idea in the second module was that you develop the concepts clearly, get the right sketches, right equations, the right assumptions, and come to the point where you know that if I have data, I need to solve this equation. In the assignment 4 that will come up, those symbols have been replaced by real numbers, and now you can actually solve the problem. So you can take your assignment and continue it further. So I'm going to take up 2 problems, one a closed system and one for an open system. So we look at a closed system where we have a cylinder piston arrangement, and what this thing is that we have a piston which is over here. It's got length is L1 over there, and what we do is we heat it, and at constant pressure the piston rises from here to here. So we are looking at a constant pressure process, and the whole thing, the piston does work. And the geometrical sum initial values are given here. The diameter of this, which is circular, is 150 millimeters. Length is about 100 mm. This length L2 is double that of L1, which means it will be 200 mm. And we will look at a case where the pressure inside here is 20 bar. So P1 is 20 bar. We will solve 2 problems. One where there is water in this, and second where there is nitrogen. So we learned that we can have a substance which we can treat as a vapor, or we can treat it as an ideal gas. So that's the differentiation we are doing, and what we want to know is what is the work transfer and heat transfer in these processes. So the process of solving problems should begin always by making a sketch and defining the system boundary. So that's the sketch in state 1. This is the sketch in state 2. And where is the system boundary in this? We say that the system boundary here is this one, and in state 2 the system boundary became like that. The system includes all the substance which is enclosed in this arrangement, excluding any of the metallic parts or any other parts that are there. So this is what it is, and we are going from state 1 to state 2 pressure constant. And to do that, we know that we'll have to heat it, and then this will go. So the first step was to define the system and get the system boundary correct. So after looking at this, it is crossing the system boundary at all with the same mass which is expanding. So important thing here is that we know this is a closed system. This is from what we have learnt in the very first module. And then we realize that if this is a closed system, the type of equations, the form of the equations that will be there is to have the control mass approach. Which means that if I have to write the first law equation for this, here we will write Q12 is equal to W12 plus E2 minus E1. It looks like a very simple thing to do, but I find that there are very many people who make mistake right here. Instead of writing this equation, they will write Q dot Cv is equal to m dot H1 plus m dot H2, all of that. So if we go wrong at this point, everything else is completely wrong. So be very clear that to understand what the system we are looking at, make the sketch and say, well, this is what it is. And this is why we will use this particular type of an equation. So now we are on the correct path here. And what we have been asked for is what is W12 and what is Q12. That's our objective. And we then proceed the same way. We say what is conservation of mass telling us? It only tells that the total mass of this and this is the same. There is no addition, there is no subtraction. So mass in the system boundary or the control mass, this is constant. We can calculate it from specific volume if that is there. No, there is a question there. We will come back to that question later. Let me just do this part. Okay, conservation of mass. Then we have conservation of energy. Okay, so the equation is the same that I have written there, and there is no assumption that is coming up in this part. And we make now we say that what are the reasonable assumptions in this application? We say that these two are such that kinetic and potential energy changes are not happening, it is stationary. The center of gravity of the system rises very slightly, and that we can neglect. So we explicitly say that we assume that delta KE is equal to delta PE, and this is 0. Which means that this E, which was U plus PE plus KE, these two terms will drop out, and we now get Q12 is equal to W12 plus U2 minus U1. And what we can see now here is that W12, this can be calculated by integrating PdV, for which we need pressure as a function of volume. In this case, we have been given P equal to constant, but that need not be the case. We could even solve the problem by saying that PV to the power n is constant, where n has a certain value. We could put that. And then this integral can be evaluated. But we need to go from state 1 to state 2, which means that we need to fully have all information about state 1 and all information about state 2. Then we say, well, how do we calculate? So that will give us the work, but to calculate heat, we need to calculate this term also. And for that, we need to know fully states 1 and states 2. We need to know all the properties in these two states. So let's see what do we know about the states. To do that, we need to know first what is the working substance. And now we'll solve the problem assuming that water is the working substance. And for state 1, we have been given that pressure is 20 bar, so P1 becomes 20 bar. We need a second property, and let's say that the second property is given to us that the quality of water in that is 0.8. So now we need to calculate all the other properties there. Say T1 is the first one, specific volume, and U1 and V1. We start the last one, which is straightforward, that the volume initially is pi d square upon 4 multiplied by L1, and d is given, L1 is given. You can do the calculation, and this is 1.766 into 10 to the power minus 3 meter cube. Please make sure that you write the units at every step. T1, it means that this is a saturated state. So T1 will be saturation temperature at 20 bar, and this is 212.4 degrees Celsius. Okay, then for V1, we'll get this is Vf in state 1 plus x1 plus Vfg in state 1. Vfg is Vg minus Vf. So, although there are two terms looking here, but they are one and the same, all we needed to know is what is the pressure, because we know it is a wet state, and we can get those numbers from the tables, and this number is 0.0799. So we get Vf and Vg, or Vf, Vg and Vfg, all are at 20 bar. And we calculate this part. Then we will need the specific internal energy, and we do exactly the same type of a calculation. This is UF at state 1, x1 UFG at state 1, and when we do the complete calculation, this will be 2261.5 kilojoules per kg. Okay, so this is what we got now, V1 also. Now we say that to calculate U2 minus U1 that we wrote over here, we need this U2, U1 can be calculated by mass times U2 minus U1. Okay, so this is, for that we need the mass, and this could be, mass is constant in the system. So to calculate that, we now have the equation there, that M1 is equal to V1 upon specific volume at 1. And this we can calculate, and this becomes 0.022 kilograms. Now we go to state 2. Here we have P2 is constant, which is given as P2 equal to P1, so this is 20 bar. And volume, we are told, has doubled, so whatever V1 we had, or we can independently calculate this as pi square upon 4 into L2. This becomes 3.532 into 10 to the power minus 3 meters. And from there, we get that V2 is equal to twice V1. And so this tells us that this is 0.1598 meter cube per kg. Now, state 2, we got P2 and we have V2. These are independent properties, so everything is completely specified. So we have to now go back and say, well, how do I get the remaining property? Now, temperature, so we make a quick check and say, how does this V2 compare with Vg at 20 bar, which is P2? So we go to the tables and pick up Vg, and it turns out that Vg at 20 bar this is 0.09958 meter cube per kg. And what we have V2, which we just calculated here, was 0.1598, which is more than this. So this means state 2 is superheated. So we go to the superheated property tables and find out that at what specific volume at 20 bar, what is the temperature that gives that. That T2 comes out to be 435.2 degrees Celsius, and from there you can also get U2 as 3004.63 kilojoules per kg. In many property tables, U2 is not given, but H will always be given. So what we need to do is do an extra calculation. We get H there, and say that U is equal to H minus PV, P and V are also given. So one extra calculation is involved if U is not explicitly given in the tables or in the property packages that we have. So we got this, and now we have everything that we needed for state 2. We can now move on and say, well, in our big scheme we wanted to calculate work. So let's write down what is the work in this process. This is integral 1 to 2 PdV, and this is P1 or P2 because pressures are both the same, V2 minus V1. So when we do the remaining calculation, this will become 20 into 10 to the power 5. Remember, this is Pascal multiplied by the two volumes that we had, 3.532 minus 1.766 into 10 to the power minus 3 meter cube. I am writing the units at every step, so please keep that in mind because quite often people go off when they mix units. When we use Pascal and meter cube, the answer will be in joules. If it was a polytropic process, this would have worked out to be P2 V2 minus P1 V1 upon 1 minus N. And remember, this was independent of the working substance. So even though we had water here, if we said that the water was undergoing a polytropic process, this would still have been okay. But we have to make sure that P2 is in Pascal and V2 is meter cube. If you are looking, and this also should be in the same units. In case we are looking at specific work, instead of V2, this will be V2, this will be V1, in which case the units must be meter kg. So it's a good practice to write the units at every step. It takes a little effort, but then you are very less likely to make a mistake. And even if you make a mistake, that's okay. We can quickly go back and check where the mistake was if things have been done very systematically. So this, we can say, this becomes 3532 joules or 3.532 kilojoules. So this has got a positive sign. So this is work done by system on surrounding. Okay, so the next step is then we just put everything together in the equation we had right in the beginning, that Q12 is W12 plus MU2 minus U1, 3532 joules plus 0.022 kilograms, which is the mass, multiplied by the difference of internal energy, 3004.63 minus 2261.5, and these units were into 10 to the power 3 joules per kg. This joules, this also has to be joules. And when you do the calculation, this will tell us this is 19881 joules, or this is 19.88 kilojoules. So we have our answers now. The result, that the work in the process, work output was 3.532 kilojoules, and heat transfer, this is also positive, this was also positive, 19.88 kilojoules. Okay, so we have solved the problem. A couple of things to think about. Firstly, where did we get this property data from? And we have many sources. You can look up the web. There are online property tables. You can look up one book, it has got property tables, another book that has got property tables. And these numbers could be slightly different depending from the source that you have taken up. Fortunately for us, for many substances, all of them will have the same reference state. So that means for water at triple point temperature, T equal to 0.01 degrees C, HF is equal to 0 and SF is equal to 0. But still, because they all are based on data fitting and then making a curve on it, the values given by different programs will be slightly different. So instead of this, it could be within say plus minus 2 or 3 kilojoules per kg. That's okay, as long as throughout the problem we use the same property source. And I'm writing this because the solutions that I have provided are based on one particular source that I am using. You could be using a different one and your numbers could be slightly different. That doesn't mean that you are making a mistake. But what is important is that up to the point of formulating the equation, if you are same and okay, then you are on the right path. The numbers could be slightly off here and there, that doesn't matter, but they won't be largely different. There are only a couple of cases where numbers will be very drastically different, and that is for certain refrigerants where the reference states have been chosen differently by different sources. So what will happen in the calculation is that values of H and S and U, which are all dependent on the reference state, they will be different. Values of V will be the same everywhere. That's not going to be an issue. These will be different, but don't worry too much about it, because in most of the problems, whether it is heat transfer or work transfer or say a throttling process, we are always dealing with difference of two properties, and the difference of two properties will be pretty much close to one another irrespective of what the reference temperature was. So you could have slightly different values of individual properties, but the difference in the properties will not be very much. So don't worry too much about it at that point. The difference should be matching with what we have. The second issue would be there is how much round off should be. And here again, if you round off at the first step itself from 3 decimals to 1 decimal and then calculate, the final answer could be somewhat different from what is there. That doesn't mean that you did a big mistake. Your process up to the first step was right, you are in good shape. The numbers you did, they could be slightly different. Round off you did differently, that could be slightly different. That's okay. The thing to remember is that when you look at property data or any property source, the number of decimal places that they give are there because they are confident that that many decimal places are okay. The next decimal place is in doubt. So if something gives value of say a specific value of R as 0.2978 kilojoules per kg per Kelvin, it means that 8 is okay. The next place of decimal you are not sure about. So if you are multiplying it by mass and your calculator gives you 8 places of decimal, nothing beyond this decimal actually makes sense. So you can safely truncate it or round off up to that many places of decimal that your original numbers had. But if you are multiplying this by 0.22, and now you have a problem, or you are multiplying it by 0.5, then the next decimal place is in doubt. So even if we get 4 decimal places from here, this multiplication tells you that you can round it off and keep only that many decimal places as the highest value that you have. So again, that you round it off at every step to the best possible number of significant places, and the final answer you can put it there. In the real world, this would mean we are able to discriminate 1 kilojoule in 1000 kilojoules. Rarely do we get this type of exactness in the real world of experimentation, and so you may even actually end up making some more rounding offs from further this point. But in this course, keep that in mind, make round-offs at every step as appropriate. Please also make sure that you write the units at every step that you do. That way you will avoid, there are quite a few people who say that when you do PV type of a calculation, pressure they take in bar, where it should have been taken in Pascal, and the complete answer goes haywire. The process is okay, you are at least 90% correct, the last number would be only at 10%. Okay, so this is what was there for water in this system. Now we go back and say that instead of, if I had nitrogen, so nitrogen is now a different ballgame altogether, and we say that nitrogen is the geometry of the device is the same, pressure is same 20 bar. Question is, for knowing state 1, either I need to know the mass of nitrogen or the density of nitrogen or specific volume or temperature. So what we will do is we will assume that temperature of nitrogen is same as what was there in the temperature of water. Doesn't have to be though, but just for comparison's sake, it will tell us that is at the same pressure and temperature it was nitrogen instead of water, what happens to the system? So we take that this is given to us. And in ideal gas equation of state, remember all temperatures have to be in absolute values, Kelvin. So we immediately convert this into 485.57 Kelvin. We will need values of the gas constant for nitrogen, maybe Cp0, Cv0. These are all given in property tables, and we take these to be constant for the entire states that the process undergoes. Okay, so then we start saying that the equations that we derive, they are still exactly the same. They do not depend on the working substance that we have. Okay, so here it is what it is. This part of the problem solving had nothing to do with what was the working substance in it, but it had everything to do with which equation we should be solving. So this process is very important. And here we will say that for nitrogen also it is exactly the same thing. Work is also integral PdV. It doesn't depend on what the material was. Internal energy change is also mu2 minus v1. This is also true. So this sheet or this part of the solution of the problem is practically independent of what the working substance was. The differences started coming in later on. So let's see what happens now with nitrogen. It tells us that the integral PdV is going to be exactly the same. We have a constant pressure process, and so this we can write as 3.532 kilojoules. If this was PV to the power n equal to constant, then we would have done exactly the same thing and written that down over here. It depends only on P2, V2 and T1, V1. So we will now also there need to know what is the final pressure and volume in the case of nitrogen, and from there we will have to calculate the work. So for that we would know what is state 1. State 1 pressure is given 20 bar. Mass we can calculate from there, P1 V1 upon RT1. We are assuming that this is what an ideal gas behavior. And throughout the process, in every state, the gas behaves like an ideal gas. So that's what we are taking here. When we put this in there, this is 0.0243 kilograms. The mass remains same in the system. In state 2, this becomes M1 is equal to M2. And so from here we can convert M into PV upon RT, and we say P1 V1 upon RT1 was mass at state 1. This is P2 V2 upon RT2. And when we solve this, we get that T2 is equal to 2 times T1. T1 has to be in Kelvin, so this becomes 971.14 Kelvin, or you can write 971.1, that's still okay, good enough. Okay, so we got T1, we got T2, and what we now need is U2 minus U1. The formula for this is same as what we had earlier. This is M U2 minus U1, and this is equal to MCV0 T2 minus T1. CV0 value will come from the property tables, and if we do the calculation and substitution, this is 8.12 kilojoules. Please remember that units have to be maintained in this calculation when you write everything. Mass has to be in kg, CV0 is say joules per kg per Kelvin, and both temperatures in Kelvin. So if this was joules per kg Kelvin, your U2 minus U1 will be in joules. If initially we took it at kilojoules, we must consistently keep kilojoules and make sure the final answer is also in kilojoules. So this is, we get the change in internal energy, and substituting that finally in Q12, this becomes W12 plus U1 minus U2 minus U1, and this is calculated as 12.45. Please remember that when we write this or we write kilograms, this K is always a lower case. It should never be a capitalized. So writing kilojoules as kj or kilogram as kg, both are wrong. Okay, so we solved the problem, and you can see that this solution methodology was different. We used a different set of things. The main thing was equation of state, and the same process for two different substances we have been able to solve it. The next example I give is of a flow cycle that we have now talked about yesterday a bit. And here is the cycle that we will look at. In the problem set, I have given some simple problems there. There are more practice problems we can give. So what it is we looked at yesterday is basically a Rankine cycle, and that's the same thing I have drawn. And we say that what is flowing in this is water, H2O. And the cycle consists of four components: a boiler, a turbine, a condenser, and a pump. And we connect these by pipes, which we will put there. The exit of the boiler to inlet of the turbine, there is this pipe. The flow is in this direction. The turbine exhausts the steam and comes into the condenser, where it flows over tubes carrying cold water and becomes saturated liquid and comes down. This flows into the inlet of the pump, which flows into the boiler. In a real power plant, some of these pipes could be like 100 meters long, 150 meters long. Some pipes could be small. For example, this pipe could be just like about 3-4 meters. And this would be even smaller than that. So that doesn't matter for us. And we are given that the turbine has inlet conditions of 200 bar and 400 degrees Celsius. It expands to 50 degrees Celsius. Then it is condensed to saturated liquid. And we want to know what is the work output of the turbine, heat input into the boiler, the cycle efficiency, what is the heat dissipation rate in the condenser, what is the power required for the pump. All these are required for selecting these equipment when we want to put the cycle together. So all these calculations have to be done. And these states tell us what is the pipe diameter and the material and the type of pipe that you are going to put for these types of conditions. So the cycle as such, what we are going to do now, is the basic first step that one does in the design of any power plant or any cogeneration system or any combined cycle power plant or any other place where such a flow system is done. It could be a refinery, a paper mill, anything. This is the first diagram that is made, and you put mass balance and energy balance on this and work out what are the parameters that you are getting in this. So we do that for this particular cycle, and the way we will do it is that we first say that there are 4 states, and we will say that this is state 1, here we have state 2, this is state 3, and here state 4. And we are assuming that in this pipe there is no change of state. So we are assuming that pipes are ideal flows, no friction, no pressure drop, no heat transfer with the surroundings. In reality, there will be a slight change, decrease in pressure and temperature because it may lose heat if it is above ambient temperature. For this analysis, in this course, we assume that to be constant. And then what we will do is, we will plot all of these into a table. So we make a table where in the first column we write down which is the state point that we are looking at. So we have 4 states, 1, 2, 3 and 4. And beside this we will list all the properties for that particular state. So first we will put pressure and units as bar, then we'll get the temperature in degrees Celsius, dryness fraction if applicable, specific volume, meter cube per kg. In a flow system we know that internal energy is not coming into the equation, so we can say that I will only worry about specific enthalpy kilojoules per kg and specific entropy kilojoules per kg per Kelvin. And now let us first write down what do we know about this system. The first is the pressure is given at state 1 as 20 bar and the temperature is given as 400 degrees Celsius. And if we look at the property tables, we know that this becomes superheated, so dryness fraction is not applicable. So this is now we are starting to infer what we from this information. So this is not applicable, and since these two are given, we can go to the property table, get the specific volume, we can get the specific enthalpy and write it there. From the table we can get the specific entropy and we can write it over there. So these we calculated. This is what was given to us. What more is given to us? In state 2, we are given that it is temperature is 50 degrees Celsius. And to know what is the state, we see that the flow has gone through the turbine, which means that we use the condition that an ideal turbine S2 will be equal to S1. And so this value will come here also, 7.129. This came here. With this and this, we compare it with the saturation specific entropies and find that this is in the wet state. And so we calculate from there and say that for this thing, dryness fraction comes out to be 0.871 and the pressure is the saturation pressure at 50 degrees Celsius. This is 0.12352. Again in bar. Some of these tables will give it in kilopascal. We have to convert it and then put it here. And specific enthalpy, again we look from the table, this is 2284.06. So now state 2 is known completely. The next thing is what happens at state 3. We are told that it is completely condensed and becomes saturated liquid. Cooling is a constant temperature process, constant pressure process. In this case it is saturated state. So wet substance going in, condensing, this is a constant temperature process. It will go to saturated liquid. That means X is equal to 0. So this is saturated liquid. And now from here, we can again go back to the tables and pick up everything that we want. The pressure is known, which is the same pressure as this one, 0.12352 bar. Specific volume, 0.001012 meter cube per kg. Specific enthalpy from the tables, 209.34. Then we come to state 4. So, well, this is at the outlet of the pump. We know that the outlet of the pump, the pressure has to be equal to the pressure at the inlet of the turbine because the process of heat addition is constant pressure. So that tells us that this will be equal to P1. So P4 equal to P1, and that across the pump entropy remains the same. So S4 is equal to S3. So from there we can now start putting things here that this is 20 bar. Dryness fraction not applicable. We know this is a compressed liquid state. We need to know the specific enthalpy, and for that we will use the relation in pumping. We have a liquid state only. H4 minus H3 is equal to P2 minus P1. So we will write this as P4 minus P3, and this could be either V3 or V4, doesn't matter because this specific volume doesn't change. We do this calculation. H3 is already known to us. H4 will come from here, which is 211.35. So now all the specific enthalpies are known to us, all the states are known, and we can visualize this cycle on the TS diagram. So this is state 1, which is superheated above the critical point, 400 degrees Celsius. This is state 1. The turbine process is isentropic. We have assumed that it comes down here to state 2. Then condensation is constant pressure, constant temperature. It comes to state 3. Then isentropic compression, it comes there. And then we have this whole process. This is the heat addition process. So that's our, by looking at it, we know that this is a Rankine cycle. And we now then just go back and put all the values in there. And for each equipment, we will write the equation and solve it. But we don't need to do it every time. We can say that globally, the common assumptions for every equipment in this is that there is steady state and that changes in kinetic energy are equal to 0 and changes in potential energy are equal to 0. Every equipment has one inflow and outflow, so the mass flow rates are same, and then we can calculate Q dot in the boiler. This turns out to be 151,852.5 kilowatts. And the way we do that is that this is m dot H1 minus H4. Similarly, you can calculate the turbine work output. This is 48,217 kilowatts. Work to the pump minus 100.5 kilowatts. And thermal efficiency, the thermodynamic efficiency, this is turbine output minus pump input divided by heat supplied to the cycle, and this turns out to be, in this case, to be 0.316 or 31.6%. And we can also do another check that we know that if it is a cycle, the second law told us that cyclic integral of heat is equal to cyclic integral of work, and you can check that by taking all these numbers that can indeed the case. Sometimes it may not be exactly the thing, one last digit could be off, but that's because of round off that has been done. So no need to worry about that part. So that's how we can solve this thing. And on the diagram itself, the way people would put this data is that we say that here we will write the state, here we will write the pressure, the temperature, the specific enthalpy, and the mass flow rate. So we write the 4 numbers here. Similarly, we can write the 4 numbers here, 4 numbers over here, and 4 numbers here. So this very important information, which is the starting point of design of such systems, contains all the information that we require to say, for instance, buying a pump. And so we say that I need so much mass flow rate, I'll give some margin on it, I need this as the inlet pressure, this as the outlet pressure, which are the pumps that I should buy. This will tell us that this is the flow rate, these are the inlet outlet conditions, which is the boiler that one should buy. Same thing with condenser, same thing with turbine. So these are the things that are the beginning of the designing and then finally putting together of a system like this one. Real systems will have more components than this, but the process that I have just mentioned is same for all of these. Okay, so that was the examples that I have given. Now we'll continue taking questions, but before that, there's one question from an earlier lecture. Somebody asked what is the difference between the Gibbs free energy or Helmholtz energy. So let's have a few minutes on that. This is a picture that summarizes the 4 energy properties that we have learned. U is the energy needed to create a system. It is the internal energy of the molecules. H, we've learned, is this plus work needed to make room for it. The different language that is there, it's slightly different meaning. Helmholtz free energy, which we call A, U minus Ts, This is this minus Ts. This is so this is energy needed to create a system, which is U minus energy provided by the surroundings or the environment. And G, which is Gibbs free energy, this is H minus Ts, which is the total energy required to create the system, make room for it, which is H minus energy provided by the surrounding, this part. So those are the four types of energies that will come in thermodynamics. And it's not just in this thermodynamics that it will come in, but they will come in, say, mixtures, reacting systems, everywhere. These are the four things that we will come across. Okay, so that was another question pending from previous lecture. And what I will do now, we'll take some time to summarize the course. What is the scope and what is it that we are hoped to achieve. So let's now do a summary. So I structured this so that we get the basics of thermodynamics up to a point, and we do it in a systematic way. So the first thing we did was to learn about concepts and definitions. We came across many of these, and while initially we just defined them, as we have gone along in the course, we saw that we were freely using these words again and again. And we could use that because the meaning is very specific and the context in which we were using it, that is clear. For example, the system boundary. We know what that is. What is the control volume? We defined what is the reversible process. We said what is thermodynamic equilibrium? What is mechanical equilibrium? So we got all those things clear in our mind that look, this is what it means, and the meaning and the definition is irrespective of the working. It is the same. So that's formed the basis for the next step, where we looked at the laws of thermodynamics. And in this, we also mentioned that we are looking at what is called a classical approach to thermodynamics as opposed to a statistical approach to thermodynamics. And here we get this important distinction that we will look at every working substance as a continuum, which means that a large number of molecules can be taken together and we can assign certain properties to it. And when we say property, we now know from concept introduction what is property. When in solving the problem, we use the word state, it means what is it that we mean by state. Laws of thermodynamics, the zeroth law, the first law, which is conservation of energy, the second law, which tells us, the zeroth law just told us about the concept of equilibrium or in temperatures being same. The first law told us what we mean by conservation of energy. While many people would say energy cannot be created or destroyed, that's a very loose definition. We now know that we will not use that. We say that cyclic integral of heat is equal to cyclic integral of work, or for a process, Q12 is equal to W12 plus the change in energy. So those are our exact statements now. We don't use energy cannot be created or destroyed. And then we went on to the second law analysis, where we got two statements, but the only mathematical equation from which we started working was the Clausius inequality. And we had two statements. Okay, so they were both in some sense negative statements. But then we sat down and said, okay, if Clausius inequality is to be valid, then if I have one of these statements and I want to make a modification to be in, so that I don't violate Clausius inequality, then what do I need to do? And so we went out from there and we came out with two concepts of a heat engine and what we may call a refrigerator or a heat pump. So what we did was they said, okay, we are going to make a process runs in a cycle, which is what Clausius inequality was telling us about, and what do we need to have as the essential components of a heat engine? That there has to be a high temperature source which gives heat to a system which is operating in a cycle, and you have to reject some energy to a low temperature reservoir. In the process you get work. So this was the necessity why TH and TL has to be there. And the way we saw it at the end of the course is that if it's a Rankine cycle, this happens, this process is the condenser process. In all the Otto cycles, diesel cycles, Brayton cycles, gas turbines everywhere, this process is replaced by expulsion of gases from the system and taking it, that goes at a high temperature, we throw them out and we take in fresh air at a low temperature. So that's what we have done, essentially replaced this of a closed system by an open system. But this law tells you that there is no way you can get rid of a condenser. And we made one comment though, that if this energy which is going out is used for other purposes like heating or cooling, then we can use that energy completely. We can say, for example, take steam from the Rankine cycle we just made and said, I won't expand it to 45 degrees Celsius, but I'll expand it to 80 degrees Celsius and use that steam for heating everybody's house or giving it for cooking. So I don't have a condenser. That is perfectly fine. It doesn't violate the laws of thermodynamics. But to say that it has got efficiency of 100%, that meaning of efficiency is different from the thermodynamic efficiency of a cycle. That process is no longer a cycle. This is a cycle. So that's one modification we saw here. Then we said the same thing about a refrigerator, that if energy has to be pumped out of a low temperature body and sent to a high temperature body, that has to be done only by the input of work. So if you are air conditioning, say for instance, a train, the coach of a train, then you are taking energy out of the coach and throwing it out into the surrounding air. For that you need electricity, and that is given either from diesel generator sets on the train or from battery or from other generators which are on the train. You are consuming electricity. And if this train were to be running in a tunnel, then we are dumping energy into the tunnel air, which is the air going out is like you feel from an air conditioner outside, about 45, 50, 55 degrees Celsius, and gradually Earth's temperature is about 23, 24 degrees Celsius, and if you keep dumping energy into the tunnel, the Earth surrounding that will be getting hotter and hotter slowly, but after 10 years, 20 years, 30 years, the Earth will become very warm, and then the only thing to do is to air condition the whole tunnel. So now you would be doing air conditioning of a tunnel to remove heat dumped by the air conditioning of the coach itself. And that's what you have to do actually in systems like metro railway systems. You have to air condition the whole tunnel. But that is where this thing came from. So we learned about this. In the process here, we developed new properties like specific internal energy, enthalpy, and in this case, specific entropy. For the purposes of solving problems like we have been doing, this knowledge is adequate. And in the first course, this is, if you learn this properly, you are in good shape. Subsequent things about availability, exergy, Gibbs free energy, all of that will follow, but that's not entirely essential at this point of time to do this basic analysis of all these thermodynamic systems and various processes. So this is what we did in the second module. Then we went to the third module and said, how do substances behave? Up to this point, both of these are independent of the working substance. It just gives you the concept in an absolute sense, which is always true. We cannot make any compromise on any of these. Then we looked at properties and we said we'll first look only at a pure substance. In a more next advanced course in thermodynamics, you would look at properties of a mixture, air and water, or maybe ammonia and water, or say butane in air, those type of things. So that requires the same basic starting point, but we start adding more things to it and develop the theory on that, and we get equations and various formulations for solving those problems. So that would be a future course. Right now we are only looking at a pure substance. That means only one type of a molecule, and that we said could be a solid, liquid, or a vapor. And under some conditions, solid and vapor can be in equilibrium, liquid or vapor can be in equilibrium, solid, liquid, and vapor can be in equilibrium, and there is one state where all three are in equilibrium, and that gave us the idea of a triple point, and we came up with the idea of a critical point as two important states for a given substance where these are fixed. There is no change in that. So we can look up tables and pick up critical points. And then we said that a pure substance could behave like a liquid and then gradually start behaving like a vapor, and then finally we said behaves like a real gas, and finally ideal gas. And we said that ideal gas, simplest thing, PV is equal to RT, the equation of state. If two independent properties are known, the state is completely defined. That's a starting point. And then we said if you have to have a real gas, we make a change and we say PV is equal to ZRT. Z is the compressibility factor. And then as we start getting closer and closer to what we have defined as a new thing, a saturated state, Z is quite a bit different from 1 for many cases, and then liquid, it is way out from 1. And then we learned that these properties versus these properties come from two different sources, but it's a part of the same situation. This comes from tables, where you have liquid plus vapor and superheated vapor, and this comes from compressibility chart and ideal gas equation. So we said this will be sort of a vapor behavior, and this the gas or an ideal gas behavior. And most applications that we have come across in this course, it will be entirely either here that the states lie in that, or entirely in this. This we call vapor cycles, this we call gas cycles. So Rankine cycles, that like we saw that, or the refrigeration cycles, they come here. Otto cycle, diesel cycle, Brayton cycle, they come here. We haven't gone into details of that, but it's only one little step more that you understand what are the process that happen one after the other, and that's a cycle. And in this course you have learned how to analyze a process, and you can just add on to it and make the complete picture. So this is what we learned as to where we get the properties from, how people measured it, how people made equations out of it, and how we get tables or software packages that tell us these data. The only important thing that came out was in the saturated state, that when it is saturated, pressure and temperature are positively correlated to one another. They are not two independent properties, and so one of them would be, any one of them would be enough to calculate the other one. And then we came across a whole bunch of properties here, pressure, temperature to begin with, then we have a dryness fraction, specific volume, specific internal energy, specific enthalpy, specific entropy. And we said that in a saturated state, these two are not independent, but any two of these will always completely specify the state. And in solving problems, we saw that somewhere we got V and U. We said, okay, now I know that the state is fully specified. I can calculate the others. It may be a little difficult to calculate, but the state is completely specified. Somewhere we get P and H, somewhere we get P and S, but we have the confidence that I have two independent properties, state is fully defined, and with a little bit of effort, I can get all the properties. So that's what we learned in the third module. And then now in the last module, we have put all these things together and said we also learned how to do a systematic problem solving. That we first define the problem, right? Identify open or closed system, equations, assumptions, and bring the equation to a point where we know that this is what I have to solve. And until that point, we are not getting into numbers. There is no need to get bogged down in doing lots of calculations, but first to get the process right, think through it, and then say, okay, now let me start putting numbers, and where will I get the numbers from? So that's what we have done here. And we also looked at some common devices or equipment which come across in this thermodynamics course. And we had a whole list of them, like boilers, turbines, and all of that. And we said that what does it do, its purpose or its function, and in thermodynamics, what is the next best assumption that we can do to make its analysis a little simpler. So we said that the simplest way to look at a boiler or any heat transfer process or a condensation process, constant pressure. What about a turbine or a pump or a blower or a fan? We say, well, we'll consider the ideal case to be isentropic. A pipe connecting these devices, we said it's an ideal flow, there is no pressure drop in the pipe. So in the beginning course, those are the assumptions which are fine. We have also seen that in some of these cases, especially work producing devices, we defined the isentropic efficiency, and we know how we can calculate the states and various things if the isentropic efficiency is given. Real machines, none of them are isentropic, they will all have something less than 1. So we looked at all of that, and now we are ready to solve a whole family of problems, look at concepts, even create systems that, say, if somebody poses to us, we know how to go about tackling it and how to put things together. In the design process, we do a thermodynamic analysis, and that gives us the starting point to select different equipment, put them together, and make a system. Okay, so that's what we have learned, and so that's in a nutshell a summary of all these lectures that I have. Okay, so let's take now questions. There's the question here. Okay, then there are a bunch of questions about availability, and I have not dealt with availability in this course, and I've deliberately done that. We will leave it to the next subsequent course. Let's stick to the contents of the course that we are looking at here. Is the second law of thermodynamics an absolute law? I don't know what you mean by absolute, but yes, there are no exceptions to the second law. Okay, we'll take it that way. Only those processes that are non-equilibrium, there might be a little issue, but as long as we are dealing with any real substance, second law of thermodynamics is absolute. What is the sense of negative entropy? Okay, so let's look at this. There are two issues in this. When you say negative entropy, one could be that the value of S that we get, especially from tables for many substances, that has a negative value, so many kilojoules per kg per Kelvin. No need to get worried about it, because this has happened because we decided that at a particular temperature, a reference temperature, we decided that HF will be 0 and SF will be 0. So take for instance, say ammonia, that reference temperature there is say minus 40 degrees Celsius. Water is 0.01 degrees Celsius. And for different substances, we can pick that. And we do that because it's only a constant offset from all the properties. So what happens is, if you take water at HF of water at 0.01 degrees Celsius to be 0, at temperatures less than that, H and S values will be negative. So that is because this was taken as a 0. Okay? if we decide that for all substances at temperature equal to 0 Kelvin, an absolute 0, HF will be 0 and SF will be 0, then no value of SF will ever be negative. They will all be positive. The only reason we don't do that is because if we do that, if we are working in temperatures like 300 Kelvin, 400 Kelvin, 500 Kelvin, all the values of specific enthalpy, specific entropy, specific internal energy, which are dependent on the reference state, they will all get added by a certain number. For example, on a TS diagram, if your reference temperature is here, we take this as 0 and we make this drawing over there. And then if we shift the reference temperature, then all of these will move here and all the values will be much larger than what we have been dealing with over here. So instead of values of few hundred and a few thousand, which we are getting in most of the tables, we would end up getting values which are in tens of thousands for every state. So unnecessarily, every number will become very big. Answer will be the same at the end. That is not the issue, except that for a physical feel for numbers and the actual number that you have to write in each calculation, they become very, very big. And that's why we don't take properties at 0 absolute Kelvin, 0 Kelvin, as the reference temperature for all substances. It would make sense for something like helium, whose triple point is very close to 0. That's a different issue. But for any other substance where the triple point is much above and the critical point is even greater than that, this doesn't make sense. It's just a matter of convenience and nothing wrong with the fact that the values were negative. Okay, so this is one interpretation of what you mean by negative entropy. Now let's look at the other thing. In a process, if the entropy decreases, so starting point state was 1 and the final state was 2 and S2 minus S1 is negative, what does this mean? Well, we did see a process like that. That we said that if is a TS diagram, if I would state here and state there and say a cooling process that brings it over there. If there is no work transfer in this, we know that delta Q is equal to TdS, and when we do that calculation, we will get that the heat transfer is T times S2 minus S1. And the chart itself shows that S2 is less than S1, so S2 minus S1 will be negative. What it tells us is that in a process where there is no work transfer but only cooling taking place, entropy change will be less than 0. Okay, so it's not a universal statement that entropy always increases. Let's not look at it that way. There are processes where entropy does decrease. Work transfer devices, entropy will always increase. If you are heating it, the process will be exactly the opposite of this. It goes from there to there. Entropy has increased. So this negative entropy change has a meaning which is like this, and this negative entropy means it's entirely because of the convenience of a reference state. So that's what these two are. Okay, so that hopefully answers your question. Okay, there's a question here which says, what is the difference between minus VDP, between VDP and PDP? Okay, so let's look at two things. One, we have a cylinder piston arrangement like the problem that we just solved. The piston is here and it slightly goes up at some point. We take a very incremental change. So there's a small change in volume and we say that during this change the pressure was constant. So the work done was PdV. But this is state 1 to 2. Then we say, okay, now the piston moved up a little bit more, the infinitesimal small amount, and the work done there then would be PdV 2 to 3. And why PdV? Is because the force is acting on the piston. This is causing a displacement of the system boundary from there to there. So there is work done at the system boundary. Okay, so that's what has happened here. And like this we keep on adding all of these and finally we get this would be integral PdV from the initial state to the final state, whatever. In that little change, we assume that the pressure was constant and it pushed the piston down. Now this is work done by the gas on the piston. What the piston does with that work can be a slightly different story. In all the analysis that we have been doing, we have been saying that assume that there is no friction between the cylinder and the piston. No leakage. In reality, some will be there. No friction. So if you look at the piston and see what happens to that force, if there is friction, this is where it got force coming from the substance, the friction acting in this direction, and the connecting rod or whatever was there acting there. So there will be a frictional work done by the piston, which is part of the work done by the system, and then piston doing this work. So there's this work done, PdV integral, minus the friction work. This will be the work output of the piston. That's a different ballgame. We then go into dynamics and machine design and all of that. So that's not coming in over here. Okay. So that is integral PdV. Now what happens in the flow system? When we looked at a pump or a blower, we said that flow is going in, going out, and our system boundary is over there. And this is the symbol of the piston. The pump. Pump or a compressor or a blower, doesn't matter. It's a flow system. The thing is that here this was a closed system. This is an open system into which flow is coming in and going out. So the equation that comes out for this particular case is the full first law equation, and if we simplify by neglecting potential energy changes, kinetic energy changes and from steady state, then you will get W dot, and there's no heat transfer also, W dot CV is M dot, say this is state 2, this is state 1, or this is the exit inlet, say HI minus HE. We can calculate HI, HE from the table if you want. But what we do here is we exploit the fact that we have another equation, TdS is equal to dH plus VdP. This is a relation between properties. So it's always true. We are assuming that the pump to be isentropic and adiabatic. So this part is become 0 and dH is minus VdP, and if we integrate this, you would get this one, and only in the case where V is constant, that means the fluid is incompressible, then dH becomes H2 minus H1 becomes minus V P2 minus P1. And that's what we put in over there as the work. So the work in this then becomes VdP work. So that's what this work was. And this V is either here or here, doesn't matter. It is the same specific volume. It's just the change of pressure that comes into play. So what has happened is VdP work comes in when there is flow, and PdV work comes in when it's a closed system. That's one difference. And if you have to plot these on a property diagram, here is what they would look like. So this side is P, this side is V, and the process started from here and it went up to there in the cylinder piston arrangement. The PdV work will be area over here. Integral VdP work will be area over here. Okay, so that's the difference. Okay. Then there's another question here. Is there a difference between heat and work? Okay, that's the next question. Well, we started thermodynamics right from the first lecture by saying that we are going to look at the thermodynamic definition of heat and work. And we said that even defined heat work, we first need to make the system boundary and then ask what is the work, what is the energy transfer across the system boundary. So heat was defined as that form of energy that crosses the system boundary because of a temperature difference. So it is a transient process and you can see heat only at the system boundary, nowhere else. And we define work that you have pushed the system boundary out or in whichever way that there is a force into the displacement that the force causes. So this is the most general form of definition of work, and you can say that any form of energy other than heat is work. Electricity is work because we have charge flowing across a potential difference, F dot ds applies. Same with magnets, same with stretching of a wire or a rubber band or compressing something, all of that is F dot ds. So there's the fundamental thing without which this whole analysis will get nowhere. Throughout the examples, everything, whenever I have talked of heat, this is the thermodynamic definition of heat, not what we learned in school. So it's very, very important that we know what is the system, what is the system boundary, and only then we can start talking of heat and work. Otherwise, there is no context of heat and work in thermodynamics. Okay? Okay, there's a question there. Do we assume quasi-static process in steady flow system analysis? Okay. So the question is, do we assume that there is a quasi-static analysis in steady flow? Yeah, and the answer is yes. Steady flow, basically what we are saying is that nothing is changing with time. And that's what we say. And this flow means that it is an open system through which flow is taking place. So this is applicable essentially only to an open system, whereas this could be for either open or closed system. So for instance, if the piston is moving, when we say at any one particular instant I will look at what is happening in the piston, we say okay, it is quasi-static, or we can say quasi-equilibrium in that condition, and then we can assign properties to it. Okay, so remember that equilibrium is a necessary condition to talk about a state which is characterized by the properties. So if something is changing with time, the next best assumption we can make is that okay, I don't have equilibrium, but I will assume for a very short duration of time that we do have equilibrium. We call that as quasi-equilibrium. Once we do that, we are legitimately talking about state and property. So that is the importance of this. Okay, the question here is reason of not using Carnot cycle practically, except that none of the cycles give 100% efficiency. Okay, so the question is, why not we use Carnot cycles in practice? The reason for a closed system and an open system I described yesterday. What happens in an ideal gas or in a closed system? The problem really happens with the fact that we need isothermal heat transfer. With gases, that is not possible to do because either you are compressing and very rapidly cooling at the same time, or expanding and heating at the same time. Both cannot be done. So isothermal heat transfer in a cylinder piston arrangement is not possible. The only thing we saw that in a flow case, when we had phase change, then we had isothermal heat transfer. But then it was a very restrictive thing, so we did use phase change as the heat rejection process in many of the devices. But there is some devices where we are to heat it, that was not possible. So that is where again there was an issue with isothermal heat transfer. And so we said that we are first heating water from liquid to saturated state to superheated state. During this process, temperature increases. That means you are adding heat to the substance as its temperature is increasing. It is no longer isothermal heat transfer, so we cannot get the Carnot cycle. So apart from the fact that you cannot exactly get 100% efficiency in isentropic process in the real world, this is the main reason why we modified isothermal heat transfer in gas engine to either isobaric heat transfer or isochoric heat transfer. And here again we said isobaric heat transfer. And the moment we did that, we sacrificed something, and so our efficiencies are always going to be less than Carnot cycle, even on the theoretical basis, assuming every other process to be reversible. Okay, there are two questions about entropy. Does entropy always depend on heat, and entropy of universe always increases? What does it imply? Okay, so the relation of entropy is not just with heat, but what has happened is entropy is some sort of a way we are trying to give a numerical value to irreversibility. Heat transfer across a finite temperature difference, we are causing some irreversibility, so it gets associated with heat. But ultimately what is happening, say in the case of say a turbine or a compressor, what is happening is because of friction in the fluid and friction between the fluid and the solid, overcoming that friction, we are dissipating energy, which is work, but that is then becoming what you may call heat or adding to the internal energy. And this is causing entropy to increase. So in general, you can look at it this way, that wherever you are looking at irreversibilities, you are looking at increase of entropy. There are some cases where irreversibility could be less, somewhere where it is much more. For example, the example I gave right in the beginning, that if you want to make a cup of tea by boiling water, would you use a source of heat? So you have a vessel there, and I have to heat it up. So I have a source here, here there is water, and I'm evaporating it at say 100 degrees Celsius. Should I have 101 degrees Celsius, or should I have 400 degrees Celsius, or should I have 100.00001 degrees Celsius? Okay, now you can see that when you do this to heat it, there is a big irreversibility associated with this. With this, the irreversibility is less. With this, the irreversibility is even less. But practically, we know that if I heat it up by 1 degree difference, it will take me a whole day to heat this up. And that's no fun. So, to reduce in the practical world, the rate at which processes happen, we do go for finite rates of change, and that brings with it irreversibilities. Okay, so that was, and the other was, yeah, okay. Okay, entropy of the universe is increasing. What does it imply? Well, what has happened is we said that this is the system, this is the surrounding, and if there was a heat transfer this way or that way, the entropy change of the system we calculated, ds in the system. Then we calculated ds of the surroundings, and we found out that in one case the temperature is more than the other temperature, so the sum of these is always greater than 0. So that's what we are saying, that the change of entropy of the universe means everything put together, so this was increasing. So that's all we are saying, that by doing irreversibilities, we are adding heat to the surroundings.
Sir, I want to ask a question. What is third law of thermodynamics and where it is applicable?
Okay, I have deliberately not gone into the third law yet, because what you need to learn right now is to learn the basics of thermodynamics and learn how to solve problems thoroughly. So please don't get too carried away with things like third law, perpetual motion machines, exergy. Those are for a future thing. So just learn what we have done, and please learn this very thoroughly. Okay. Okay, there is a question. Is it possible to use diesel in a petrol engine? I suggest you just go and try it and see what happens. Look up the properties of diesel, whether it will burn or not, and then see what happens. And you can also look at it in a very practical way, that if it were possible, people would have started using diesel in their cars, because diesel is cheaper than petrol. The fact that they don't use it means that there is a problem with it. Okay, so we'll conclude here. We are saying that we have covered basics of thermodynamics, which you need to know very well. After that, there is various types of thermodynamic topics that can be covered up. But for most practical applications, this is the beginning part with which we should be very, very thorough. and you have done that, that's your job well done. Okay, thank you.